Monocular 3D reconstruction is a fundamental challenge in computer vision, but current methods are unnecessarily complex. In this video, we explore PointDiT, a minimalist pixel space diffusion transformer that simplifies the entire pipeline. By operating directly on raw 3D point maps, PointDiT eliminates the need for complex hybrid architectures and lossy latent-space tokenizers. We will break down how this model achieves state-of-the-art geometric accuracy and sharper boundaries using a plain vision transformer trained from scratch. To understand the breakthrough, we must first look at the limitations of existing paradigms. Deterministic regression models tend to predict the mean of the output distribution, which oversmooths fine geometric details. On the other hand, latent diffusion models rely on variational autoencoders, or VAEs, to compress 3D data. However, VAE compression is fundamentally lossy, introducing reconstruction noise that caps the final quality. PointDiT is designed to bypass both of these limitations entirely. The core breakthrough of PointDiT is its minimalist, pixel space architecture. Instead of compressing the geometry, PointDiT treats the 3D point map as a multi-channel image and operates directly on raw patches. The noisy point map is patchified and linearly embedded into tokens. These tokens are then processed by a plain vision transformer backbone. This direct pixel space approach preserves high-frequency details that are typically lost in latent spaces. Stable training in pixel space requires two critical design choices. First, instead of predicting velocity, PointDiT uses an X-prediction objective, meaning it directly predicts the clean point map at each step. Second, standard logit normal noise schedules rarely sample a time step of exactly 0, creating a train test discrepancy. PointDiT resolves this with a rectified sampling strategy, randomly setting the time step to 10% of the time to calibrate the model. To guide the 3D reconstruction, PointDiT conditions its generation on the input RGB image. Rather than using a standard image embedder, the model extracts features from a frozen, pre-trained DI-No v3 encoder. Crucially, it combines features from 4 intermediate layers to capture both low-level details and high-level semantics. These image tokens are concatenated with the point map tokens, providing robust, domain-invariant visual cues. The experimental results demonstrate that PointDiT outperforms complex latent-based models. It achieves the sharpest geometric boundaries, measured by the BF1 metric, across multiple real-world datasets. Qualitatively, PointDiT excels at reconstructing thin structures, like chair legs, and resolving depth in highly ambiguous regions, such as transparent glassware. It achieves this superior detail without relying on intricate, handcrafted loss functions. A unique advantage of PointDiT is its flexibility during inference. Because of its strong pixel-to-pixel alignment, the model can perform competitive single-step feed-forward inference, acting like a deterministic regressor. However, if higher quality is needed, users can run multi-step diffusion using the exact same network. Each additional sampling step steadily refines the local details and sharpens the geometric boundaries. While PointDiT represents a major step forward, some limitations remain. The model is currently trained at fixed resolutions, and its performance on outdoor scenes is slightly limited by the diversity of its synthetic training data. Future work will focus on scaling the training set, enabling mixed-resolution training, and extending the architecture to jointly output RGB appearance and camera parameters alongside 3D geometry.